Okay, so obviously last time we were talking about electron configuration, and we're going to continue on. So remember that you can recreate this on the paper for yourself pretty easily. That in combination with what we talked about earlier, that s orbitals could hold a maximum of 2 electrons, the p subshell 6 electrons, the d subshell 10 electrons, and the f subshell 14 electrons. Again, should allow you to pretty much write any type of electron configuration that you need to do. Remember, you always want to start here and just kind of keep zigzagging back around after you finish sort of the arrows. And that will get you your correct order. So we left off with carbon, I think. So we're going to do nitrogen next. So nitrogen has 7 electrons. And again, that would be 1s2, 2s2, and 2p3 in this case. That again means that nitrogen has, on this second energy level now, 5 electrons, 3 and 2. And again, still on that first energy level, the maximum it can have, which is 2 electrons. Now, when we draw our orbital diagram, again, I'll try to write everything towards the top to make it easier to see. We will go 1s, 2s, and again, we would need 3 lines or boxes to represent our p subshell. And again, it's going to go up, down, up, down. And as we talked about there towards the end last time, there's Hund's rule, which says when you have multiple orbitals within a subshell, we're going to try to maximize parallel spin, which means they're all going in the same direction. So what again that means is we would put these electrons, one in each of these orbitals facing upwards, and we do go left to right in this situation, and that would be our orbital diagram. We can now see that the p subshell has how many electrons left to fill? Could fill 3 more, right? So we could continue on until we would then have to kind of go to the next step. So let's continue on and take a look at those. Might as well finish out the first 10 since we're on a roll here. Why not? Go. The next one is oxygen, which once again, we are going to start here to the 1s. We're going to zigzag back to the 2s, and where we're at right now at the 2p, basically zigzagging there. So once again, 1s2, 2s2, 2p, I was going to say 6. That didn't seem right to me. So that's 4. 4 sounds good. I can do math. All right, so if you count up the top ones, again, that is how many electrons we put in there, 2, 4, 8 electrons. Once again here for our orbital diagram, we'll use our lines. And again, we're going to go up, down, up, down. Once again here, up, up, and up. At this point, we have no option but to go back to the left here. And now we're going to start pairing these electrons off by putting that last one in the top left spot. We now have 6 electrons here in the second energy level. And again, our 2 that max out our first energy level, right? Any question on that one there? All right, continuing on here to fluorine, I think should come next. So fluorine at 9 would be 1s2, 2s2, 2p5 at this point. Once again, looking at our orbital diagram for this. Again, not drawn energy correct. We're just going to go side by side here to save space so you can see it. We will go up, down, once again, up, 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 and now we come back down, and now we put our next one there in the center. That, as you can see here, leaves us basically one more spot until that subshell is filled at this point, right? As we can see here is fluorine, second energy level. We have 7 electrons, 2 in the s orbital on the second energy level, 5 in the p orbital there on the second energy level. All right, to finish out the top 10 here, we're going to go to neon there to finish it out. And now neon is going to be 1s2, 2s2, 2p6 in this case. Again, our orbital diagram here for neon. All right, if I put an E there, now it's neon. There it is, 1s, 2s, 1, 2, 3, 2p. So again, we're going to go up, down, up, down, up, 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 and now come back and pair. Pair it up, and pair it up. Can I put any more electrons there in the p subshell? I am full at this point, which means if I did have more electrons as we came through here, zigzag back, we would zigzag back. Our next stop on the train would be obviously our 3s orbital is where those electrons would go next if we needed to fill it. Question on orbital diagram, electron configuration. So when you are asked to draw the orbital diagram, that's what you should draw. Lines and arrows or boxes and arrows. Don't draw shapes like circles and figure eights or anything like that, okay? So why don't you try this one here? Why don't you do argon's electron configuration? See what you get, which is 18. We're going to start up here. So we're going to go 1s, swing back, 2s, and keep swinging this way until we get to where we need to be. So let's take a look at this here. We're going to go 1s2, 2s2, 2p6. Again, if I count up the top numbers, that is 10 electrons. I got 8 more to go. We're going to then go 3s2. That's now 12 electrons. And now we could get into our 3p6. That should now be 18 electrons. This guy has how many electrons on the third energy level? 2 and 6 make 8. So it's got 8 on the third energy level. It's got 8 on the second energy level, which fills up the second energy level. And it's got 2 on the first energy level, which fills up that energy level. If we're doing our orbital diagram, we would need a 1s box, a 2s box. We would need a 2p box, 3 of them actually. We would need a 3s box and a 3p box. And it would go in like this, up and down, up and down, up, 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 down, 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 up and down. And once again, this would feel the same way, up, 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 down, down, and down in that case. Any questions on that there? So if we look at something, say, one of the ways that electrons basically go into the atom is the same idea as was sometimes referred to as the off-ball principle. And that is basically protons are added to the nucleus one at a time, and electrons are added to the atomic orbitals. Basically, is the same idea, one at a time, lowest energy to highest until they are filled. Now, if we look at something like potassium, for example, and we write the electron configuration, which is 19, we would have a 1s2, a 2s2, a 2p6, 3s2, 3p6. That is 18. And by the way, if I look at my little guy, wherever he went there, we are now filled the 3p. Our next stop here is again the 4s. So as we talked about earlier, remember that the 4s is actually lower in energy than the 3d. So the s's come before the d's. And that is a very common mistake that people make. At this point, they will jump to the d's thinking logically 3d would come next. But again, because of that shift in energy levels, it is actually the 4s that comes next. And that is what we're going to use next to finish out our configuration here, which is for this guy. And it would be 4s1 in this case. Yeah. Now, when we look at the electron configuration for potassium, up until this point in the configuration, how many electrons is that? That is 18 electrons. You could get it by counting the top numbers. So that is basically 18 electrons. And again, you could get that by counting all the top numbers here. Now, when we look at the periodic table, number 18 is what element? We just did this electron configuration a second ago. It is argon. We could do a shorthand for the configuration by putting argon in brackets. And what that means is that is the electron configuration for argon. And then we could just continue on with the electron configuration as 4s1. So this is what is known as argon 4s1. Whatever goes in the bracket always needs to be a noble gas, right? Because argon is the noble gas. So if you want to do this shorthand, you have to look on the periodic table and you have to find the noble gas that comes right before the element you want to write the electron configuration for, and that would be what you would put in brackets, and then you would continue on. For example, if we did our friend sodium, which is 11 electrons, 1s2, 2s2, 2p6, 3s1. Up until this point on sodium's configuration, that is 10. And if we look on the periodic table, the noble gas that comes right before it is neon. So we could shorthand this neon 3s1. So sometimes it's referred as to writing noble gas configuration when you do an electron configuration. Again, always needs to be the noble gas that goes in the brackets and always the one that comes before whatever you're trying to write, basically the electron configuration for. Any questions on that shorthand there? Okay. Now let's talk a little bit about transition metals, which as we know are between group 2 and group 3 on the periodic table. They are basically our D sort of subshells. They have incompletely filled D subshells or give rise to ions that have incompletely D-filled subshells. Remember, though, that they are the third energy level. So again, the order here, when we get to transition metals, especially the first row transition metals, we will fill the S's first and then the D. So again, that is how the electrons will go in as you get into the transition metal, especially the first row, Sc, TIF, chromium, and all those guys. Now, there is two exceptions to the normal electron configuration for transition metals, and I'm going to write it towards the top so it'll be easier to see. Those two exceptions are chromium, which is 24, and copper, which is 29. Now, if you follow our little chart that we've been using and write the electron configuration for these two guys, you will end up with an electron configuration that looks something like this, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And for copper, you will end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. And this is the configuration that you would get as you go through our little chart. It has been found experimentally that they are more stable with one less electron in the s orbital and one more in the d. So it kind of goes upwards to the d orbital. The same sort of exception happens here in copper. It's actually one more up. They could do that because the 4s is actually super close in energy to the 3d, which means it does not take a lot of energy for this electron basically to kind of go upwards. And actually, as we will talk about a little bit, what actually happens in terms of energy is as you start to fill the 3d orbitals up, they actually switch in energy. There's actually a switch in energy that occurs between those as d orbitals get filled. So the correct electron configuration for chromium, and I'm just going to shorthand it. So if I look on the periodic table for chromium, and I go back to the noble gas that comes before chromium, which one is it? What noble gas comes before Cr? That is argon, I hope, right? Ar, that comes before it. That means that I could take this part of the configuration, right? And that's going to be argon's configuration. And it will be 4s1, 3d5. So that is the exception. One more electron up in the d orbital, one less electron in the s. And I could do the same thing for copper. If you look on the periodic table, copper is also the noble gas that comes before it is argon as well. That again is this part of the configuration. And I could shorthand this argon 4s1 3d10. So what does this do for chromium? It actually maximizes the parallel spins, right? It puts all those single paired electrons going in the same direction, makes it a little bit more stable. It pairs off for copper, the d orbitals, and leaves an unpaired electron in the s, which also makes it a little bit more stable. There is a lot of exceptions to the electron configuration in the transition metal region. If you go where chromium is and copper on the periodic table, and if you go down and in, there's a ton of exceptions, like silver is an exception, PD is an exception. For example, PD has no electrons in its s orbital. They've all went to the d and stuff. So there's a lot of exceptions kind of in that transition metal region below copper and chromium and in. For us, in most chemistry classes that you take, these are the two that you're responsible for. And that will be for us too. So these two are the ones that you're responsible for. You should just know that in reality, there are some other exceptions. But for everybody else, you could write it just based on the little chart guide that we've been using. But no, it might not be correct in all aspects of it. So as you can see here, those are those two exceptions as we go through it. And just to show you some of the other ones there in the transition metal region, those are chromium, copper. And as I showed you before, I said a second ago, you can see PD actually has no electrons in its s orbital. They've all been basically one up there. So for us, once again, it is only chromium and copper that you are responsible to know, and you should write the electron configuration like there on the right-hand side, one electron in the s, extra electron in the d. Everybody else, you can write the same. Now, speaking of transition metals, I will get to that in a second. Let's talk about the lanthanide and actinide series. The lanthanide and actinide sort of series are those guys on the bottom. Those are the two rows on the very bottom of the periodic table. That is where our F subshells begin. And they could have incompletely filled F subshells and ions that give rise to incompletely filled F subshells. This is a periodic table, the ending for everybody. And once again, if we kind of zoom in maybe a little bit there, you could see some of those exceptions here, silver, palladium I was talking about, some of the other exceptions happening over there as well. So a lot of them underneath chromium. Also, this guy is an exception. So once again, only chromium, copper you're responsible for. But as you can see here, there are a lot of exceptions that kind of fall underneath those guys. Now, let's talk about the periodic table and electron configuration. If you know what you're doing, you could use the periodic table to write electron configuration or count it off. So when we look at the periodic table, there are period numbers 1 through 7. If you remember, our N, right, goes 1 through 7. So those period numbers represent that principal quantum number, the energy levels of 1 through 7. They correspond to that. When we look at group 1 and 2 on the periodic table, they correspond to the S block. How many electrons can an S orbital hold? 2, 1 and 2. So that is those two, yeah. Groups 3 through 8 represents the P subshell or the P block on the periodic table. If I filled up all the P subshell, how many electrons? 6, 1, 2, 3, 4, 5, and 6, yeah. The transition metals, which are right here, is the D block on the periodic table. D subshell could hold 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And our F block is down here, the lanthanide and actinide series on the very bottom. They could hold 14. I'll count, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 boxes. So you could actually count off electron configuration if you know. For example, let me clear all this here. Let me actually erase all. So if we look over here, this is sodium right there in that box. So if we were to count off electron configuration for sodium, you would start up here at period 1. Right here would be 1s2 to get to helium. So that would be 1s2. That would then be 2s2, those two boxes, 2s2. Over here, this is 2p6 all the way to the end. And this is 3s only 1, right? First box in, 3s1, yeah? So you could count off electron configuration like that. You know, if you had sulfur, which is right about there. So if you had sulfur right about there, you could do the same thing. You could start again with 1s2 to there, 2s2 to there, 2p6 to there. Now I'm going 3s2 because I need both of those boxes. And now this is going to be 3p1, 2, 3, and 4. And that would be 3p4. So you could count it off pretty good going through this. Let's just say, though, that I wanted to do iron, which is right here, right? So I want to do iron, which is right there. Get rid of all that there. All right, so we're going to count here, right? So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What comes after 4s2? That's the D, right? D start on what energy level? 3. This right here is not 4D. This is actually 3D. It is 1 behind the period number. That would be 4D, 5D, 6D going downwards. So this should be 3D, 1, 2, 3, 4, 5, 6. And that is what it should go. So again, remember that the D start on 3. It is 1 behind the period number. If you should get down here, this is 4F on the very bottom, which really goes right here. That is 2 behind the period number. The F guys on the very bottom are actually 2 behind the period number. So I don't know. I personally would still use the little chart. It probably will not make you mess up. If you get into the transition metal region here, you got to really watch out for that again with the 3D and coming back 1 behind, but you can count it off on the periodic table if you want to. Any questions on how to do that there? Okay. So let's talk a little bit about a couple of things here. I'll find a spot I can draw. Let's talk a little bit about what happens when something gains a charge. So let's take our sodium, for example, that we've written this electron configuration before, which is 11 electrons, 1s2, 2s2, 2p6, 3s1, right? Now, when sodium gains a charge, it is group number 1, which means it should make a +1 charge, as I think we talked about in chapter 4, I think we did. When it has a positive charge, it means it has lost electrons, which means sodium with a +1 charge will have only 10 electrons. And that will give me an electron configuration of 1s2, 2s2, 2p6. That again is 10 electrons. Who on the periodic table is number 10? Neon, right? So I'll have the same electron configuration as neon when it has a +1 charge. If I look at nitrogen, which has no charge, or if it has no charge, has 7 electrons. It has a 1s2, 2s2, 2p3 in its terms of electron configuration. When nitrogen, which is group 5 on the periodic table, gains a charge, it is a -3 charge that it gains. That means it has gained 3 electrons, which means it will have a 10 electrons in nitride, and it will have an electron configuration of 1s2, 2s2, 2p6, are again neon's configuration. What we see here is sodium, nitride, and neon. They all have the same electron configuration. That is known as being isoelectronic with each other. So things that are isoelectronic have the same electron configuration. When sodium lost an electron, it ended up with the same electron configuration as neon, which is a noble gas. When nitrogen gained 3 electrons, it ended up as the same electron configuration as neon was a noble gas. Noble gases are extremely stable, and it really is the purpose of all types of bonding, like ionic bonding and covalent bonding, is for everybody to have the same electron configuration as the noble gases. And this is how metals and nonmetals, when they come together and make an ionic compound, get to a noble gas configuration. Metals will lose their electrons and back up on the periodic table to the noble gas that comes before them. Nonmetals will accept electrons and go forward on the periodic table to the noble gas after them. And that's really the whole basis of why bonding occurs, is for everybody to achieve noble gas configuration, to have the same electron configuration as a noble gas, because that is really stable. Does sodium with a +1 charge and nitrogen with a -3 charge, do they actually become the element neon? They do not. They only, again, have the same electron configuration as neon. They are still sodium and nitrogen because they have the correct number of protons. They have not changed any protons, so they're still those elements. They're just much, much stabler because they have achieved that configuration. So why don't you do the electron configuration for sulfur with a -2 charge, which is sulfide, and why don't you do aluminum with a +3 charge? Okay, so let's take a look. So here, sulfur with no charge has 16 electrons to match its protons. Here with a -2, again, the minus means it has gained electrons. The 2 is how many it gained. So basically, if you take 16 plus 2, that's going to give you 18 electrons. which means the sulfide ion would have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6 in this case. That is the same electron configuration as 18, which is our friend argon's configuration, right? So it has the same electron configuration as argon. By gaining those two electrons, becomes really stable. Question on that one there. Here, if we look at aluminum, it has 13 electrons in its neutral state, plus 3 charge. The plus means it has lost electrons. 3 is how many it has lost. So 13 minus 3 is 10 electrons. So our aluminum ion should have an electron configuration of 1s2, 2s2, 2p6, or that is our friend neon. So typically speaking, when you are dealing with representative elements, which are the guys to the left and to the right, metals and nonmetals of the transition metal region, they typically will lose those last electrons in their configuration, or they will gain electrons into those last orbitals, and that's where they're able to sort of accept them. Now, let's talk a little bit about transition metals and when they actually make a charge. So transition metals are a little bit different in terms of what happens. And I'll just use the same page here and right towards the top so we can kind of see it. Now, with transition metals, when they make ions, as we talked about before, the 4s, for example, in the first period of transition metals gets the electrons first, and the 3d would then get the electrons next. What happens when we start putting electrons into the 3d orbitals? There's actually a switch in terms of the energy. So obviously here, energy going that way. And what ends up happening is the 4s orbital actually ends up being higher in energy than the 3d orbital. And this happens only with transition metals. As they start filling those d orbitals, they actually switch back. This is why, on a side note, that if you ever Google like electron configuration or you look at it and stuff like that, you will sometimes see people write electron configuration all in order, it looks like. They'll put all the 3s together, the 3s, 3p, 3d, and then go to the 4s. The reason they do that is because that electron configuration, the way they wrote it, is based on energy. No chemistry class that you take, including this one, writes electron configuration like that. Every chemistry class that you take writes it based on filling order, how the electrons go into the atom. And based on filling order, it is the S first and then the D. So that's why you should write it in here, like we talked about, the S's come first and then the D. But in real life, you will sometimes see people write it the other way, and that is based on energy. But you should always write it based on filling in this class and any chemistry class you take. I've only taken one chemistry class ever in my life that we wrote it the other way, and most of them we write it the exact way that we talked about, and that's the filling order. But there is an importance to this switch in energy that occurs. And where it comes into play is when transition metals lose electrons. Because electrons, when they are lost, they are always lost from the highest energy orbital first. So if we took something like iron that we wrote the electron configuration for, I think a second ago, that is 26. And that would be 1s2, 2s2, 2p6, 3s2, 3p6. Again, 4s2 first, 3d6. We could also shorten it again with our argon, 4s2, 3d6. Now, when iron, for example, makes a positive 2 charge, how many electrons does it have? It will have 24 electrons in this case, right? Because it lost 2. Now, basically, if we draw in what iron's orbital diagram looks like for just the last part of it, it will look something like that. And we could see that it is actually the 4s electrons that again are higher in energy because of this switch that occurs. So when iron actually loses its electrons, it will actually lose these 2 electrons first. And that will make the configuration for iron with a +2 charge as argon 3d6. We're going to actually lose those s electrons first. By the way, if they need to, they also can then start losing d electrons as well, because those would be the next. So transition metals actually have the ability to lose their s's, which they always lose first. But if necessary, they can then dig into the d orbitals and also lose electrons. For example, if we take iron and it has a +3 charge, how many electrons? 23 electrons it would have. It will once again lose these 2 electrons here. But that is only 2 electrons, right? It needs to actually lose 3. The next highest in energy is their d orbitals, and it will lose its 3rd electron right there out of this guy. It will lose that electron. And its configuration would be argon 3d5. So transition metals are different because they actually have more valence electrons. They have a lot more electrons they could lose. And they will go from the S first, then into the D. They are also different than representative metals like sodium, potassium, calcium. They do not end up at noble gas configuration, right? They're far away from noble gas configuration. They actually don't end up there. Something like iron would have to lose like 8 electrons to end up at noble gas configuration. And you don't typically see an iron with an 8+ charge. It just really doesn't happen. So they typically will not end up at noble gas configuration, transition metals, and they will lose, once again, their s electrons first. So why don't you try one? Why don't you do Mn with a +2 charge and Mn with a +4 charge? What will be the electron configuration? Mn on the periodic table is 25. Let's take a look and see. So why don't we start with Mn with no charge, has 25. We work the electron configuration for that guy, 1s2, 2s2, 2p6, 3s2, 3p6, again 4s2 first, 3d5, I believe there. Again, this can be shorthanded as argon for up to here, 4s2, 3d5. Any questions on the electron configuration of Mn with no charge? Now, if we go to our Mn2+, that means it has lost 2 electrons. So this guy will only have 23 electrons. Now, if we kind of fill in our orbital diagram here for just the back end, we have this, and we have 1, 2, 3, 4, and 5. Remember, there's going to be that switch that's going to occur because it's a transition metal, and we will end up with ultimately what we have here on the right happening. So that means that the first electrons, the 2 that we should lose, is going to once again be our 4s here. Again, going to lose those first. So those will go away. And that will leave us in a configuration, if we did the shorthand, argon 3d5. Any questions at that there? Are obviously 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. So basically just take that out of the configuration and you will have the proper one there for that. Now, if we go to Mn with a 4+ charge, it now will have 21 electrons, right? Because it lost 4. Once again, it's going to take those 2 out of here. And now we still have 2 more to go, which means we are going to take 2 out of here, right? So we're going to take 2 out of that and going to dig out of there. And that will leave us argon 3d3 in this case, yeah. R again, everything like here, and make this 3d3, get rid of the 4s2. Question on transition metals, yeah. Every transition metal will do this, basically, yeah. Yeah, so not really the S's first. So just I want to go back to this chart here where I think this was a good one to look at. Or where did I do that there? Blocks there. Actually, it's this way. It's after this, I think. Right here. So when we look at this one, for example, where we're talking about sort of the blocks, right, and all that. So transition metals are pretty much here, all through here. So right before them always are s electrons, right? So all transition metals will always basically lose those s electrons, and most of them, especially the first two rows, will then dip into the D's there for any more that's necessary at that point. So transition metals always will lose those S's and then cut into the D's. Yeah. Other questions on that there? Yeah. It is. And it's your shortcut for 18 and beyond until you get to basically 36 and beyond. Then krypton will become your shortcut. Yeah. So it's always got to be that noble gas that comes before. Yep. Other questions? Okay. So now that we talked about that, let's talk about valence electrons. Valence electrons are important electrons. They are the highest energy electrons. They are the ones that are furthest away from the nucleus and not held as tightly. And for example, if we look at nitrogen, I'll write up here, a little bit easier to see, 1s2, 2s2, 2p3. The highest energy electrons are all the electrons that are in the second energy level here, right? That's the first energy level. That is 3 and 2 make 5 valence electrons. The lower energy electrons are referred to as core electrons. Core electrons are closer to the nucleus. They are not involved in bonding because they are so close to the nucleus, they ain't going anywhere. They're so much attracted to it that they're held tightly. They're not able to be removed. Valence electrons, which are these 5 here, are further enough away from the nucleus that they are not held as tightly and they're easier to remove. Valence electrons are the ones that are involved in bonding because of that. They're on the outside ones, furthest away from the nucleus. They're not held as tight. So when atoms come together, they're like the first ones to say hello to each other, and they're the ones basically involved in bonding. So you could write the electron configuration to figure out the valence electrons. They will be the highest energy ones, will be your valence electrons. But a much easier way to figure out valence electrons is it equals the group number. So the group number on the periodic table will give you the number of valence electrons. Everybody in group 1, will have 1 valence electron. Everybody in group 2 will have 2. 3, 3, 4, 5, 6, 7, and 8. 4, 5, 6, 7, and 8. The exception to that in group 8 is helium. Helium is part of group 8, but helium has how many electrons? Only has 2, so it can't have 8. So helium has 2 valence electrons because it only has 2. Everybody else in group 8 will have 8 valence electrons, but helium only has 2 total electrons, so it can't have 8. So that's why it maxes out at 2. Now, what about transition metals? Can we do that as well? We can, and if we look at, we should have these in better location. Yeah. Where's that number? Right here. If we look at our transition metals, we actually could use the regular numbering, not the representative numbering, like the A numbering like we usually do. We could call this group 1, group 2. This would be group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then obviously 13 through 18. But just looking at transition metals, if you want to figure out how many valence electrons they have, those are the numbers. They equal the group number. So how do we get to that number? Let's take a look at iron that we've just looked at, right? Iron's electron configuration is argon, 4s2, 3d6, the last part here, right, which is basically its valence electrons. That is 2 and 6 is 8. Iron is right there at group number 8, yeah, on the periodic table. So those are its valence electrons that's available to it, even though it won't use them all. But that is what we do with transition metals. So if you want to use the group number for transition metals to figure out valence electrons, 1 through 18 numbering is what you want to use. For everybody, that's the representative elements outside of the transition metals. You use our regular numbering of 1 through 8, and where we skip the middle part. Just like we did Mn a second ago, Mn is argon, 4s2, 3d5. That's 5 and 2 is 7, group number 7. Even chromium with its exception, electron configuration of argon, 4s1, 3d5. That is 5 and 1 is 6. There's chromium right there at number 6, yeah? So you could use the 1 through 18, again, really 3 through 12. They'll never use them all, but that is technically how many valence electrons that those guys have. Any questions on transition metals and valence electrons? Okay. All right, so that is definitely a much easier way to figure out valence electrons, is just to go by the group number. So let's talk a little about some of these periodic trends that we saw today, and some of the reasons why certain guys will gain electrons, certain things will lose electrons, why things are more reactive. As we saw today, going down a group for metals, reactivity increases, like we saw in the video, right? Lithium was less reactive than sodium, sodium was less reactive than potassium, and so forth. So the order of reactivity going down a group for a metal is reactivity increases as you go down. The opposite is true for our nonmetals, which are on the upper right of the periodic table over here. And what we saw with group 7, for example, is reactivity increase going up. Going up a group for our nonmetals. And that's why I said earlier that the most reactive nonmetal you can find is upper right of the periodic table. Most reactive metal you can find is lower left of the periodic table. So why really is that? Let's take a look at really these trends, which are really important for why that happens. The first sort of trend is what is known as Z effective. This is what is known as effective nuclear charge. The general trend for effective nuclear charge is it increases as you go up and to the right, decreases as you go down. The idea here is, we'll take a look at a really simple explanation of what we're talking about here. The idea is if we take lithium, which is 3 electrons, electron configuration, 1s2, 2s1. How many valence electrons does lithium have? Valence electrons, it has group number 1. Yeah, so it has 1 valence electron. This is its valence electron right there. This is its core electrons right there, yeah? So it has 1 valence electron in the second energy level. And if we drew like a little picture of what's going on, we have a nucleus that is positively 3 charged for our lithium because it has 3 protons. In the first energy level, it's got 2 electrons, which is its core electrons near it, right? Second energy level, a little further away, we have our 1 valence electron flying around randomly, right? So the idea here is opposites attract, right? Positive and negative things are attracted to each other, and that attraction increases with the size of the charge. So something that is +3 and -3 will be much strongerly attracted to each other than something like +1 and -1 when they come together. So when we look at these core electrons right here, they are going to feel the full brunt of that +3 charge of the nucleus. They're going to be strongly attracted to it because, frankly, they're right near them, right? They're flying around randomly near them. They're going to feel that full attraction to the nucleus. But when we talk about our valence electron, which is out here, he actually experiences what is known as shielding. He is actually shielded from the +3 charge of the nucleus by those electrons that are lower in energy, closer to the nucleus. It's kind of like when you used to be able to go to the movie theater and pick your seat right in the middle. A nice seat in the middle of the movie, and right before the movie starts, somebody comes and sits in front of you with a giant cowboy hat, just shielded half of the screen, right? And that's sort of the same idea here with these electrons. That outer electron is not going to feel the full +3 charge here because those electrons in front of them get in the way, basically. You could actually calculate what that electron is feeling. And that is what is known as Z effective. And that is the positive charge in the nucleus minus the number of electrons that are shielding. So there's 2 of them in front of them. That leaves you a +1 charge. That means that this outer electron is actually only feeling a +1 attraction to the nucleus. Is that guy going to be held tighter or not as tight as those core electrons, which is feeling the +3 charge? The core electrons are going to feel the +3 charge, going to be held tighter than the valence electron that's only feeling like a +1 pull towards the nucleus. That is why those valence electron could go and participate in bonding. It's not held as tightly. So these outer electrons, these valence electrons feel shielding or experience shielding, and that causes them not to be held as tightly and easier removed and involved in bonding than core electrons. Only electrons in lower energy levels shield electrons higher in energy than them. Guys in the same energy level don't shield each other or anything like that. So that's sort of the idea there. Any questions on that? Yeah. Exactly. Only lower electrons, energy electrons will shield higher energy electrons. Guys in the same energy level, electrons, they won't shield each other or anything like that. This is also why things sometimes are electrons get pulled in tighter to one another than they are on certain parts of the periodic table. Because effective nuclear charge increases as you go to the right, even the outer electrons are going to feel a stronger positive pull. And that's why it brings everybody in closer to each other as you go up and to the right on the periodic table, as opposed to down to the left where there's not as much protons and there's a lot more electrons that are not pulled as tightly. Another really important trend is ionization energy, as I mentioned before. Ionization energy is the energy required to lose an electron. So that is the energy needed to remove an electron from the gas phase. By the way, the general trend for ionization energy, first ionization energy, is it increases as you go this way, up and to the right, decreases as you go down. Just like everything else, electrons are actually lost one at a time. They don't all just drop off at once. So for example, if we look at magnesium, the first thing that would happen is magnesium would lose 1 electron. And it will become a +1 charge. We see the electron on the product side like it's being given off. To do this, this is what is referred to as the first ionization energy. So that is the amount of energy required to remove the first electron. Then what will happen is magnesium that has lost 1 electron will lose perhaps a second electron. Also on the product side. That is known as the second ionization energy. And then maybe magnesium with a +2 charge loses 1 more electron, makes a +3 charge. That is known as the third ionization energy. So there's an ionization energy for every electron that comes off. Is it easier to remove the first electron or the second electron, do you think? It is actually easier to remove the first electron. When you lose an electron and somebody becomes positively charged, Does the size of that ion get larger or smaller than it started with? It's going to lose electrons, right? So it's going to shrink electron cloud. So every time it loses an electron, everybody moves in closer to the nucleus, right? So now they're closer to the nucleus, which means they're going to be held tighter, harder to remove another electron. Gets harder even more. Every time you pop off an electron, everybody's going to kind of continually move closer and get smaller to the nucleus. So the trend in terms of first ionization energy to second to third is it increases as you go from each of those. How much of an increase does depend on what's happening. If we look at magnesium's electron configuration, 1s2, 2s2, 2p6, 3s2. How many valence electrons does magnesium have? What group is magnesium? Mg is group number 2 on the periodic table, which means it has 2 valence electrons right there. These are core electrons. So the first electron, not too bad, maybe like 750, 900 kilojoules of energy. Second electron, maybe like 1400 kilojoules of energy to do that. It goes up. That is both of the valence electrons. When you get to the third ionization energy for something like magnesium, it is about 10 to 11 times the amount of energy needed to remove the first electron. Not going to happen. It's not energy efficient to do so. That is why something like magnesium, which is group number 2, always forms a +2 charge, because when you get to the third electron, you are now into core electron territory. Good luck trying to rip that thing off, yeah, because it is too close to the nucleus. It's even closer because it's already lost electrons, so it's moved much, much closer to that positive charge. It's not energy efficient to allow that guy to lose another electron. That is why certain things have fixed positive charges. Like everybody in group 1 has a +1 charge, everybody in group 2 is +2. Aluminum is +3, because at some point you're going to get into those core electrons and it's not energy efficient to be able to rip those off. Any questions on that there? So general trend in first ionization energy is it increases as you go up and to the right and decreases as you go down and to the left. Another important trend, and as you can see, here's magnesium actually, 735 for the first electron, about 1400 for the second, and now you're about 7700 to try to rip off that core electron. It doesn't do it. Look at aluminum, which makes a +3 charge. You go from 580 for the first one up to 11,600 to try to rip off a core electron, and again, it's just not going to happen based on energy. Another important trend is electron affinity. Electron affinity, as I mentioned before, is the energy change when somebody gains an electron. And on the periodic table, it increases as you go up and to the right, decreases as you go down. Electron affinity means you have an affinity for something, you like it. It means you like to gain electrons. So things that have a really high negative energy change means that they typically like to gain a lot of electrons. Is this trend perfect? It is not. For example, if you look at group 7, it goes up as you go up, and then it kind of comes back down. It's not a perfect trend, but the overall general trend is it increases as you go to the right and decreases as you go to the left. And that is where we form anions. Those are guys that gain electrons. So we typically talk about electron affinity when we talk about anions. We talk about ionization energy when we talk about cations, because those are guys that lose electrons and become positively charged. Atomic radius decreases as you go actually to the right and up, and increases as you go down to the left. By the way, when somebody gains an electron, does the ion become larger or smaller than the neutral guy? It becomes larger because it gains electrons, does the opposite, has more in its electron cloud, right, as it starts gaining electrons. So the anion is actually larger than the neutral ion, or the neutral atom. The cation is smaller because it keeps losing electrons. The idea here is for the same reasons we talked about. Radius gets smaller because the effective nuclear charge increases as you go to the right. So again, even though the outer electrons are further away, there's a greater effective nuclear charge that they're feeling that's going to pull them in and make everything smaller, as we can see here. So adding to this is one last sort of trend, which is electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. And it increases as you go up and to the right. Fluorine is actually the most electronegative element you could have, and decreases as you go down. So to finish up on what all these trends have in common, if we look at them together on a periodic table, badly drawn, but we'll give it a go. We had effective nuclear charge increasing as you go this way, decreasing as you go this way. We had ionization energy, which was increasing as you go this way, decreasing as you go this way. We had electron affinity, increasing as you go this way, decreasing as you go this way. We had electronegativity, increasing as you go up and to the right, decreasing as you go down. And we had size basically getting smaller as you go up and to the right and increasing as you go down. When we look at the upper right of the periodic table, where we have all of our nonmetals, we have things that are very small in size because of the effective nuclear charge. The outer electrons are now closer to the nucleus, which means they're going to be held tighter. They have very high ionization energy, which means it takes an extraordinary amount of energy to try to remove an electron. Not going to happen. They have very high electron affinity and electronegativity, which means A, they like to gain electrons, and B, they like to bring electrons towards themselves. These are all the reasons why when we go up and to the right, our nonmetals typically like to gain electrons and become negatively charged anions. That is also why when we go up and to the right for our nonmetals, they become more reactive because they have all those trends of I'm hanging on to my electron and I'm going to try to take yours, basically. So all those trends increase as you go up and to the right. That is also why when we go down and to the left on the periodic table where our metals are, we have all the trends of the size is really big of the atom. The electrons that are further out are really far away from the nucleus. They have a very low effective nuclear charge. They're not being pulled in very tightly and not held as tightly. They have low ionization energy, which means it takes less energy to remove an electron. They have no interest in gaining electrons, really, or taking people's electrons because they have low electron affinity and low electronegativity. That is why these guys typically will lose electrons and become positively charged ions. That is also why activity increases as you go down in a group for metals because their electrons are not held on very tightly. They're like free to go. And that makes them very, very reactive because they're good to go and start reacting. Any questions?